In this section, I will show you how to use the Laplace transform to solve certain initial value problems. The method of Laplace transforms for differential equations is as follows. To solve an initial value problem, we take the Laplace transform of both sides of the equation. Then we use properties of the Laplace transform and the initial conditions to obtain an equation for the Laplace transform of the solution and then solve this equation for the transform. Then we determine the inverse Laplace transform of the solution by looking it up in a table or by using a suitable method such as partial fractions in combination with the table. So in this example, we're asked to solve the initial value problem y double prime minus 2y prime plus 5y equals negative 8e to the power negative t with initial conditions y at 0 equals 2 and y prime at 0 equals 12. So we're going to start off by taking the Laplace transform on both sides and then using linearity. So we have to take the Laplace transform of y double prime, and then we're subtracting 2 times the Laplace transform of y prime, and then we're adding 5 times the Laplace transform of just y. So we're adding 5 times, and then the Laplace transform of y, we just denote that by capital Y of S. And then we also take the Laplace transform on the right-hand side, and we get the Laplace transform of, actually, we can factor out a negative 8 because of linearity. So it's negative 8 times the Laplace transform of e to the power negative t. So now we look up in the properties the Laplace transform of y double prime, and this is equal to s squared times the Laplace transform of y minus s times y at 0, and then minus y prime at 0. And then we subtract from that 2 times the Laplace transform of y prime. And according to the properties of the Laplace transform, this is s times y of s minus y at 0. And then we just keep plus 5 times y of s. And then that is equal to negative 8 times, and the Laplace transform of e to the power negative t is given by 1 over s minus 1. So it's the at e to the power at with a equals negative 1. The Laplace transform of that is 1 over s minus 8. Okay, so once we have that, we want to collect all the terms that have a Laplace transform of y. So we have an s squared here, and then we have a negative 2s here, and then a plus 5 here. So when we combine that, we get s squared minus 2s plus 5 times y of s. Now, then we want to do something with the initial conditions. When we look at the initial conditions right here, we have y at 0 equals 2 and y prime at 0 equals 12. So here for y0, I can put in 2, and for y prime, I can substitute 12. And so I substitute 2 here as well. And then I use that to write down the rest of my equation. So I have minus 2s that's this one right here. And then I have minus 12, that's this part right here. And then I have plus 2 times 2 is plus 4. And that is equal to negative 8 over s plus 1. So the idea is now to solve this for y of s. And so we want to bring everything that does not have a y of s to the other side. And so what we get then is s squared minus 2s plus 5 times y of s is equal to negative 8 over s plus 1 plus 2s plus 12 minus 4, or just plus 8, right? This is negative 8, bring it to the other side, we get plus 8. Okay, so what we want to do then is write this as a single fraction, and we get s squared minus 2s plus 5 on the left-hand side times y of s equals negative 8 over s plus 1 plus 2s plus 8 times s plus 1 over s plus 1. I made a common denominator for these two. And when I simplify that, I get s squared minus 2s plus 5 times y of s equals 2s squared plus 10s over s plus 1. And then finally, if I want to solve this for y of s, I have to divide both sides by that factor in front of the ys. So from this, it follows that my y of s is equal to, in the denominator, s plus 1 times s squared minus 2s plus 5. And then in the numerator, we have 2s squared plus 10s. So that is my expression for y of s. And in order to break this down, we would need a partial fraction decomposition for this right here. So I would state that y of t is now the Laplace inverse of 2s squared plus 10s over s plus 1. And we have to factor this, but this expression doesn't factor anymore. So we'll actually have to complete the square there. So that will be s minus 1 squared, and then plus 2 squared. So verify that you can complete the square for that. And so if we take the Laplace inverse of that expression, we get the inverse Laplace of, and now we can write this, we can decompose this fraction as follows. It will be L inverse of A. You put that as another color. So that will be A over S plus 1. And then plus the next fraction in the denominator will have S minus 1 squared plus 2 squared. And then the variables we're going to use are b times s minus 1, and then plus 2 times c. And so if you break that down a little bit further using linearity, we actually get that this is equal to A times the Laplace inverse of 1 over S plus 1, and then plus B times the Laplace inverse of S minus 1 over S minus 1 squared plus 2 squared, and then plus C times the Laplace inverse of 2 over S minus 1 squared plus 2 squared. And these Laplace inverses are Laplace inverses that we can look up in a table. So the first one, the Laplace inverse of 1 over s plus 1 is of the form 1 over s minus a. So that is actually e to the power negative t. The second Laplace inverse is e to the power at cosine bt, where a is negative 1, or a is 1 and b is 2. So what we get there is plus, and then b times e to the power t cosine 2t, and then plus c times, and this is of the form e to the power at sine 2t with sine bt, where b is 2 and a is 1. So this is c times e to the power t sine of 2t. And all that is left to do at this point is to figure out what A, B, and C are. What are these constants? And so we have to complete our partial fraction decomposition, and that is given by 2s squared plus 10s over s plus 1 times s minus 1 squared plus 4, and that is equal to a over s plus 1, and then plus b times s minus 1 plus 2c, all of that over s minus 1 squared plus 4. And we've done several examples of that in the previous section. So you would multiply both sides by the denominator on the left. Some stuff will cancel out. Then you pick some smart choices for s, and then you figure out what these constants should be. And I would urge you to do this, to double check this, and see if you can find the correct coefficients. But what we'll see here is that a will be equal to -1, and then b will be equal to 3, and c will be equal to 4. And so taking these 4 values, plugging them in there, will then give us our final answer. So our final answer will be y of t equals negative e to the power negative t, that's our a, and then plus 3, that's our b, e to the power t cosine 2t, and then plus c, which is 4 times e to the power t sine of 2t.